Hello, it's David Archer, and this is the first module of my Antennas for Non-Specialists course. This module is the review of basic physics. We're going to talk about some concepts that you should have got in first year college physics, but hopefully it will be useful later on in this course. So I'm going to start off with this will be a quick review of first year college physics in one session. It's just going to be done quickly, just to remind you of some of the concepts you probably already have seen. The primary objective is for training your intuition on some of these concepts and the relationship between the quantities. So again, we're going to assume you've seen most of this before. It really should be a review. And then you know some basic calculus, in particular what a derivative is and what an integral is. If not, you still might get something out of this. Okay, so we'll start off with reviewing the SI units of measurement. In particular, the SI units have recently changed, and some people don't know that. And then definition of derived units that come from SI units like force, momentum, work, energy, power, voltage, etc. We will talk a little bit about Maxwell's equations, which are the equations of electromagnetics. And in particular, we'll show how they lead to a wave equation and come up with a value for the speed of light. We will talk a little bit about electric fields and power density, a section on wave phenomena, things like, what is period, what is frequency, what is wave number, that sort of thing. SI units. In 2019, so not that long ago, the 7 base units were all redefined to be traced back to physical constants. So the second is defined still by the value of a particular defined atomic transition. Meter is defined by defining the speed of light. Say this is what the speed of light is. And then you can figure out the meter in terms of that speed, so how long it would take to go for 1 meter. Kilogram is defined by setting the value of Planck's constant. Amps is defined by defining the elementary charge, which is then the amp is defined as a certain number of elementary charge passing by a point per second. Kelvin is defined by setting the Boltzmann constant. And the mole is defined by setting Avogadro's constant, the number of things in a mole. A mole is, if you remember, is kind of like a concept of like a dozen. It's a mole of things is Avogadro numbers of things. And candela is kind of an oddball one in that it's sort of defined in terms of all the other units in a way. So, what are the units of measures that can be derived from the SI units? Well, it's by taking various combinations of them. For instance, distance divided by time gives you speed or velocity, measured in meters per second. Acceleration, meters per second squared. Jerk, meters per second cubed. These are ones that are related to motion. Other ways you can combine the units. Frequency is 1 over seconds, 1 over time, and that's given the name hertz. Force, a newton, it's a kilogram meters per second. Work or energy is measured in joules, kilogram meters per second. Power, which is the time rate of change of work or energy, is measured in watts, so it's kilogram meters squared per second squared. And a volt is a joule per coulomb, or a kilogram meter per second coulomb. So as you combine these in different ways, you get different units. Also involved with the SI units are the SI prefixes, which are different from the prefixes that are used in computer science. In computer science, they're related to like factors of 2. The SI prefixes are in terms of powers of 10. So the other thing you might notice, with the exception of the K over here, for various reasons, all the units that are the prefixes that are greater than 1 have capital letters except for the K. All the prefixes that are below 1 are lowercase letters, and this is a lowercase mu, in case you don't know the Greek letter. So like a decimeter is 1/10 of a meter, a centimeter is 100th of a meter, a kilogram is 1,000 grams. So these are here for reference. You should know some of them. The other thing that you might have noticed is how you abbreviate the units. Some are lowercase, some are uppercase. A lot of people don't know this. The basic rule for units is, if the units are spelled out, they are always spelled lowercase. Meter, coulomb, bell, Newton, joule, everything. Even if the unit was named after a person. The abbreviation for the unit is lowercase if the unit was not named after a person. So that's why meters, seconds, kilograms are lowercase abbreviations for meter, second, and kilogram. The MSKG. And the capital C, B, and J are abbreviations for coulomb, bell, Newton, and joule because they're named after somebody. Many of you probably know this, but a lot of people I've kind of surprised didn't know this. So that's the general rule. If the unit's spelled out, it's all lowercase regardless if it's named after somebody, and the abbreviation is uppercase if it's named after somebody, lowercase if it wasn't. SI examples, prefix examples. You've probably heard of a dB or a decibel. It's 1/10 of a bell because the D means 1/10. So we will talk about what a decibel is later, but decibel is 1/10 of a bell. So here's some other example. 1,000 Kelvin could be written as 1,000 K or 1 kilokelvin, which is kind of one of the reasons why the kilo is lowercase, but among other reasons. 1 gigahertz is 1,000 megahertz, which is a million kilohertz or a billion hertz. Those are all represent the same frequency. And the hertz is the unit named after Heinrich Rudolf Hertz. It's 1 over a second. It's per second is the unit. F equals ma, and you can't push a rope. That's a famous saying that some people say summarizes all of physics, but it's not exactly true. So in physics, you've got in science and engineering in general, words have to have precise definitions. I mean, momentum in this case is defined as mass times velocity. So if something has a certain momentum, it's a mass moving with a certain velocity. That tells you it's momentum. Momentum is a vector quantity. It has a direction. So P equals mv. So that's a vector quantity. Like I said, boldface type indicate that these are vectors. You should have seen this before. Units of momentum, because it's mass times velocity, must be kilogram meters per second. Like I said, force. Force is defined by Newton's second law. Force is the time derivative of momentum. So F is equal to dp dt. It's the rate of change of momentum. Well, that means it's the derivative of mv. And by the product rule, it's m dv dt plus v dm dt, which is ma plus v dm dt. So wait a minute, what is this F equals ma plus this thing? Well, this is what the force is for things whose an object that's changing mass. This is needed for rockets, for instance, because they're constantly losing mass as they push their propellant out the backside. So this term is needed for describing the motion of things that have variable mass. But if the mass doesn't, if the thing doesn't lose or gain any mass, F equals ma, and this term is 0. So I can say in the special case where the mass is constant, F equals ma. Units of force are kilogram meters per second squared. This particular unit of force is given the name Newton. Again, lowercase n. The abbreviation is a capital N. Force is also a vector quantity. Conserved quantities. So there's a lot of quantities in physics that are conserved. These almost are taken as axioms, but there's conservation of energy, momentum, angular momentum, electric charge. There's all kinds of things that are conserved, but it's not important. The one that we really care about in this course will be conservation of energy, and all that really means is the amount of energy in the basically stays the same. It doesn't change. It can change form, but it can't be destroyed or created. Conservation of energy is the key thing for some of the derivations of antenna theory. Work is a 4-letter word. Work, the definition of work is basically the force in the direction of motion times the distance traveled. So in this case, it says the line integral of f dot dl, where this is over the path the object takes. You could break it up into a little bunch of linear segments, and then you can look at the component of force in that segment times the length of that segment and add them all up. In fact, that's how you actually do the integral, and you make the length of the segments go to 0. But that's basically what that is. That is what work is. The units of work are obviously then from these quantities, this being meters, this meaning whatever, kilogram meters per second squared. So the units of work are kilogram meters squared per second squared. Work is given the name, this unit is given the name joule with a capital J. Work and energy are the same thing. Basically, work is what you get and energy